California desert, summer, 1942. The air trembled with heat above the dusty airstrip at Muroc, a lonely stretch of cracked earth that would one day be known as Edwards Air Force Base. A B-24 Liberator sat at the far end of the runway, its four-piston engines straining, propellers shimmering in the haze. Engineers in khaki shirts crouched beside the wings, their hands black with soot. They had bolted something strange to the bomber's fuselage, stubby metal cylinders with no propellers, no moving parts, just conical nozzles aimed backward. The pilot's hand tightened on the throttle. A countdown echoed through the radio static. 3, 2, 1. A blinding roar ripped through the air. Fire burst from under the wings. 8 small rockets ignited at once, their exhaust trailing molten smoke across the desert. The B-24 lurched forward like a living thing, wheels lifting free after only a few hundred feet. In seconds it was airborne, climbing faster than anyone had thought possible. When the film reels of that test reached Europe, German scientists at Peenemünde watched in disbelief. America, they realized, had just found a way to turn rockets into wings. By 1942, the world was in flames, and the sky had become its most decisive battlefield. Across continents, airfields buzzed with overworked engines and anxious crews. The United States Army Air Forces had grown into the largest aerial armada on Earth. But its power had one fragile weakness: the ground. Every mission began the same way, with the struggle of takeoff. The B-24 Liberator, America's workhorse heavy bomber, was powerful in flight, but sluggish on the ground. Fully loaded with fuel and bombs, its engines groaned against gravity. Tropical heat in the Pacific, soft coral runways, and high-altitude airstrips in China made liftoff treacherous. Many aircraft never cleared the trees. Others tore through the end of the runway, too heavy to climb. It wasn't only bombers. Fighters carrying auxiliary tanks or reconnaissance equipment often needed dangerous lengths of runway to launch. In war zones where airfields were carved out of jungle or desert, too short often meant fatal. The U.S. Army Air Forces needed a miracle, a way to turn dead weight into momentum. That miracle began not in a factory, but in a classroom, at the Guggenheim Aeronautical Laboratory at the California Institute of Technology, known as GALCIT. A Hungarian-born physicist named Theodore von Kármán led a small team of researchers obsessed with a simple idea. What if aircraft could borrow a burst of rocket power just for takeoff? Their initial experiments, begun in 1936, were almost academic. Von Kármán and his graduate students, including Frank Malina, Jack Parsons, and Ed Foreman, were studying small solid-fuel rockets. They were young, brilliant, and dangerously curious. When their early engines blew craters in the ground behind Caltech's campus, the university quietly asked them to move their tests into the nearby Arroyo Seco Canyon. It was there, among the rocks and orange dust, that modern American rocketry was born. When World War II erupted, the Army Air Corps took notice. In 1941, officers from Wright Field visited Caltech, intrigued by reports of the group's miniature rocket motors. Could these engines, they asked, help overloaded planes lift off from shorter strips? Von Kármán's group said yes, but they had no funding, no materials, and no experience attaching rockets to airplanes. Still, within weeks, they were at March Field in California, strapping small powder rockets beneath the wings of a tired Ercoupe light aircraft. The first test nearly ended in disaster. The rockets fired unevenly, twisting the plane sideways, but after months of refinement, they achieved a balance. 6 steel tubes filled with solid propellant, ignited in perfect sequence. The result, the world's first jet-assisted takeoff, or JATO. In August 1941, the U.S. Army's Air Corps officially sanctioned the project. The contract read simply, Development of rocket units for aircraft takeoff assistance. The program accelerated with wartime urgency. GALCIT partnered with the newly formed Aerojet Engineering Corporation, a startup created by the same Caltech scientists to manufacture the devices. Their goal was audacious: a reliable rocket that any pilot could bolt under a wing, ignite, and discard once airborne. No guidance systems, no complex machinery, just raw thrust when it mattered most. Each JATO unit contained about 5 pounds of black powder propellant, enough to produce 600 pounds of thrust for roughly 12 seconds. The first major success came when a twin-engine Lockheed P-38, weighed down with test equipment, leapt off the runway under rocket power. Observers described it as unnatural, a machine suddenly freed from the laws of inertia. The Army ordered thousands, yet even as America's rocket pioneers built devices to help airplanes fly, a very different philosophy was unfolding across the Atlantic. In Germany, scientists at Peenemünde were developing rocket engines not to assist aircraft, but to replace them entirely. Their dream was the Me-163 Komet, the world's first rocket fighter, a plane that burned its fuel in seconds and often killed its pilot with the same violence that made it fly. Two nations, two approaches, one aimed for destruction, the other for lift. And as the war deepened, those opposite visions of rocket power would soon collide, in the minds of German scientists who thought they had seen everything, until they saw a bomber take off on fire. While American engineers were experimenting in the California desert, Germany's rocket scientists were chasing glory and desperation in equal measure. By 1942, the Reich had poured vast resources into rocket development under the supervision of General Walter Dornberger and a young, ambitious engineer named Wernher von Braun. Their program at Peenemünde, hidden along the Baltic coast, was focused entirely on weapons, flying bombs, guided missiles, and rocket-propelled interceptors. To the German mind, rockets were instruments of vengeance. To the Americans, they were tools of flight. The difference was philosophical, and it would define the post-war world. At Peenemünde, the Me-163 Komet embodied Germany's obsession with speed at any cost. Fueled by volatile T-Stoff and C-Stoff, a combination so unstable it could dissolve human flesh, the rocket fighter could climb faster than any aircraft in existence. But it was a suicide machine disguised as technology. Most missions ended with the pilot either crashing or burning. German engineers solved the problem of thrust, but ignored the problem of control. In contrast, at Caltech's GALCIT rocket research project, the Americans were guided by Theodore von Kármán's philosophy. Science must serve flight, not fantasy. Von Kármán understood that rockets would shape the future, but he insisted on practical progress. Small, reliable advances, one test at a time. Under his direction, the team refined the jet-assisted takeoff system into a military-ready device. They experimented with new propellants, replacing black powder with composite solids that burned longer and cleaner. Engineers designed detachable racks, so ground crews could mount and remove JATO units in minutes. The technology evolved from fragile prototypes into standardized equipment. The U.S. Navy joined the program in 1943, recognizing its value for carrier-based aircraft. Taking off from a ship's short deck had always required a delicate balance of wind and thrust. With JATO, even a heavily loaded bomber could launch safely in calm seas. The Navy's tests at the Naval Air Test Center in Maryland proved so successful that JATO-equipped aircraft began flying in combat zones within months. Meanwhile, Germany's scientists dismissed such developments as minor curiosities. To them, the true future of flight lay in full rocket propulsion. The V-2, a ballistic missile designed to strike London from the stratosphere. They never realized that the Americans, though slower in publicity, were quietly mastering applied rocketry. the kind that worked consistently, safely, and could be built by the thousands. Back in California, another transformation was underway. In 1943, von Kármán's GALCIT team spun off a permanent laboratory, the Jet Propulsion Laboratory, JPL, to continue rocket research for both the Army and the Navy. It was born directly from the JATO project, a fusion of wartime urgency and academic curiosity. Few could have guessed that this same group of engineers would one day help send humans to the moon. But in the immediate war years, their focus was simpler: get planes off the ground faster. Field trials expanded to include the Douglas A-20 Havoc, the PBY Catalina, and the C-47 transport. The rockets proved invaluable for overloaded rescue aircraft operating from Pacific atolls, where soft coral runways couldn't support long takeoffs. With JATO, even in tropical humidity and crosswinds, aircraft launched with a confidence that defied nature. Crews described it as a kick in the back from God. By 1944, JATO units were being mass-produced by Aerojet Engineering Corporation, another Caltech offshoot. The devices were standardized, packed in metal cases, and shipped worldwide. They could be bolted to any airframe and ignited electrically. American combat footage showing bombers launching with rocket flares beneath their wings was shared among Allied commands. But one of those film reels, captured in Europe, would soon find its way to Germany. There, at Peenemünde, engineers accustomed to testing vertical rocket takeoffs stopped and stared at something utterly new: a conventional bomber using controlled rocket thrust to assist flight. It was practical, efficient, elegant. And for the first time, German scientists realized that the Americans were not just copying their technology, they were evolving it. The race for the future of flight was no longer about who could build the biggest rocket. It was about who could make one work where it mattered most. In every war, there are two kinds of genius: those who dream of power and those who solve problems. The story of jet-assisted takeoff was not born from grand visions of conquest, but from the quiet urgency of men solving one of aviation's most stubborn problems: the struggle to leave the ground. At its core, the jet-assisted takeoff unit, the JATO, was a simple device, but its simplicity was deceptive. Each unit was a steel cylinder roughly 3 feet long, sealed at one end and fitted with a narrow nozzle at the other. Inside, a carefully measured charge of solid propellant waited for ignition. When fired, the fuel burned in milliseconds, expanding into superheated gas that blasted through the nozzle, producing instant thrust. Each JATO could generate about 600 to 1,000 pounds of force for roughly 10 seconds. Mounted in clusters of 4, 6, or 8, the rockets turned sluggish bombers into sprinting beasts. The secret was balance. If the rockets fired unevenly, the plane could spin, stall, or tear itself apart. Engineers at Caltech spent months perfecting symmetrical ignition. They designed timing circuits and electrical detonators triggered from the cockpit, ensuring every rocket burst in unison. The first reliable configuration used 6 rockets, each aligned at a precise downward angle to counteract the plane's center of gravity. The result was astonishing: a 20% reduction in takeoff distance and a climb rate previously thought impossible. Pilots called it a shove from the hand of God. But beyond the physics, what made JATO revolutionary was standardization. Until then, rockets were laboratory curiosities, unstable, experimental, and deadly. The Caltech and Aerojet teams turned them into equipment. They could be packed in crates, stored for months, and installed by ground crews with wrenches. Not white coats. It was the moment rocketry stopped being theory and became industry. The men behind JATO were scientists, yes, but they were also dreamers and daredevils. The GALCIT team often tested their rockets by hand, standing dangerously close as flames roared from improvised engines. Jack Parsons, the group's most volatile genius, mixed propellants in his Pasadena backyard, surrounded by test tubes and occult books, a strange mix of chemistry and mysticism that both fascinated and terrified his peers. His early fuel mixtures, codenamed Galcit 27, became the first dependable solid propellant in history. Frank Malina, a calm, methodical engineer, translated the chaos into equations. His notebooks read like a bridge between madness and order. Thrust curves, burn times, casing pressures. Together with Theodore von Kármán's mentorship, they formed the heart of the American rocket movement. The Army Air Corps called them the suicide scientists. Von Kármán called them pioneers. Their field tests were part science, part ritual. In one early run, an overloaded A-20 Havoc nearly exploded when a JATO tube misfired. Instead of retreating, Parsons and Malina stayed at the test site all night, reconfiguring circuits by flashlight. The next morning, the plane roared off the desert floor perfectly. Behind every successful test was a string of failures. Rockets that misfired, planes that veered, engines that melted. Yet no one quit. They believed that giving airplanes rocket assistance wasn't just an engineering trick. It was a glimpse into the future of powered flight. They were right. In 1943, the first operational JATO-equipped bombers took flight over the Pacific. Their mission: heavy takeoff from coral runways on islands like Guadalcanal, Tarawa, and Saipan. Tropical conditions made long runs impossible. Without JATO, some missions simply couldn't launch. The JATO changed that overnight. A B-24 fully loaded with 6,000 pounds of bombs and full fuel tanks could now leave the ground in less than half the distance. It wasn't faster in combat, but it was there, when otherwise it wouldn't be. The psychological effect on air crews was enormous. Pilots who once feared stalling at the runway's end now trusted the thunder beneath them. Crews said the launch felt like being punched forward by an invisible giant. Tactically, this meant the Allies could operate from forward bases the Japanese believed unusable. It meant faster response times, shorter airfields, and fewer aborted missions. JATO became not just a mechanical device, but a strategic equalizer, letting geography bow to physics. The Navy's adoption of JATO pushed things further. Carrier-based aircraft, especially twin-engine planes like the PBY Catalina and later the PB-4Y2 Privateer, gained the ability to take off even in calm seas. The first successful carrier-assisted JATO launch took place in 1944, filmed in color, a spectacle of blue flame and roaring engines that would later astonish engineers in Europe. By that time, Germany was still struggling to perfect the V-2 missile, losing men and material in catastrophic explosions. America, meanwhile, had mastered the art of controlled propulsion, and though the Germans would not know it yet, they were about to be shown the film that proved it. In the waning years of the war, Allied intelligence footage of new American rocket-assisted aircraft inevitably found its way into German hands. Somewhere in 1944, at Peenemünde, the heart of the Reichsrocket program, a group of Luftwaffe officers and engineers gathered in a dim projection room to examine. Captured film reels labeled U.S. Experimental. Aircraft tests. The grainy, black-and-white footage began with a long shot of a B-24 bomber sitting idle on a desert runway. The next few frames showed fire bursting under its wings, a sudden acceleration, and an impossible climb. For a moment, no one spoke. Then murmurs broke out across the room. They replayed the scene again and again, trying to understand. To the Germans, rockets were instruments of flight, not assistance. They had spent years designing machines like the Me-163 Komet, entire aircraft driven by engines that consumed themselves in seconds. The Americans, in contrast, were using rockets with precision, modest thrust, and astonishing control. The footage rattled them. The German engineers realized they were witnessing something they had not even considered: the hybridization of flight. Instead of replacing engines with rockets, the Americans had made them partners. It was elegant, practical, and industrially achievable, everything the German system was not: technical. Reports from Peenemünde after the screening described the devices as short-duration boosters attached to airframes for assisted launch. One line captured their astonishment: the Americans appear to have achieved stable thrust ignition for multi-unit rockets, a feat not presently possible with our fuels. Their disbelief was not just about technology, it was about culture. The Germans operated within a rigid hierarchy that demanded results at any cost. Their scientists worked in silos, cut off from each other by secrecy and fear. In America, open collaboration between academia, industry, and the military had produced solutions that were safer, scalable, and reusable. Wernher von Braun, when later questioned by Allied officers, admitted his surprise at JATO's sophistication. It was the difference, he said, between desperation and discipline. Germany had chased perfection through terror. America had achieved progress through freedom. Behind every rocket fired on those dusty California airfields stood an industrial miracle. In 1942, a few students at Caltech could build maybe a dozen JATO bottles a month. By 1944, thanks to wartime expansion, Aerojet Engineering Corporation was producing thousands. Aerojet's factory floor was a cross between a chemistry lab and an assembly line. Women in overalls filled steel casings with carefully measured propellant under strict safety codes. Engineers checked nozzle shapes by hand, ensuring uniform burn patterns. Each unit was stamped, serialized, and shipped to depots across the Pacific and Europe. The innovation wasn't only in the rockets, it was in the process. America had industrialized reliability. JATO's simplicity made it universal. A unit could be bolted under any plane, transport, bomber, or patrol aircraft, and fired at will. Pilots who once needed a mile of runway could now lift off in half the distance. Logistics units began to request JATO kits as standard gear, not experimental aid. The U.S. Navy integrated JATO on seaplanes and rescue craft. The Army experimented with short takeoff cargo planes, envisioning airborne supply lines that no terrain could stop. What began as a field experiment became a doctrine: lift anywhere, fight anywhere. Meanwhile, Aerojet's rapid success had broader consequences. To manage government contracts, the company had to formalize its partnership with Caltech, a union that eventually evolved into the Jet Propulsion Laboratory, JPL, which still bears the scars and spirit of those wartime days. It was at JPL that the foundations of post-war rocket science were laid, not in secret military bunkers, but in open academic collaboration. America's scientists didn't vanish into government vaults. They became professors, engineers, and industrial leaders. When German scientists learned this after the war, they were stunned. They had assumed such technological feats must have required massive state control, hidden laboratories, and slave labor. Instead, they found that JATO, the first practical rocket system of the modern age, had been built by free citizens on open campuses, funded by military contracts, but fueled by curiosity. It was a new model for power, science organized as democracy. In every invention lies a mirror of its maker. German rocketry had produced weapons of terror. The V-2, a missile that rose through clouds only to fall upon cities. American rocketry had produced a tool for flight, a device that helped aircraft lift, not crash. The contrast was stark. Both sides drew from the same physics, the same equations, the same ambition to master thrust. But one used it to destroy, the other to ascend. When the war ended and the smoke cleared, those two paths would converge under Operation Paperclip. But at this moment in history, They stood worlds apart. For the German engineers staring at those film reels, the revelation was humbling. They had believed themselves the undisputed masters of rocket science. Yet here was proof that innovation did not belong to ideology. It belonged to imagination and discipline. The Americans hadn't just caught up, they had surpassed. And for the scientists of Peenemünde, that realization cut deeper than defeat. It was the day they understood that the age of controlled flight had truly begun. Not in Germany, but in a California desert, where rockets first learned to help instead of kill. By 1943, the war had reached a fever pitch, and the Allies needed every ounce of speed, range, and lift they could muster. The jungles of New Guinea, the beaches of North Africa, and the coral runways of the Central Pacific had one thing in common: airstrips that were too short for the massive bombers they were meant to serve. It was here, amid the mud, heat, and chaos, that jet-assisted Takeoff made its combat debut. On a humid morning in the Solomon Islands, ground crews worked feverishly around a fully loaded B-24 Liberator. Beneath its wings were 8 stubby rocket tubes, their silver casings glinting in the sun. Engineers checked wiring twice, sweat dripping from their helmets. The air smelled of oil and anticipation. Inside the cockpit, the pilot and co-pilot went through the checklist, the same ritual they'd practiced 100 times. Except today, they weren't trusting the plane's engines alone. "Ready on the rockets," came the call from the control truck. Engines roared. The bomber began to roll, its heavy frame reluctant at first. Then, the pilot thumbed the ignition switch. 8 flashes erupted beneath the wings. For 10 deafening seconds, the airfield turned to chaos. Fire, dust, and thunder. The bomber shot forward like a slingshot released, the nose lifting cleanly, wheels leaving the ground long before the runway's end. In the control tower, observers erupted in cheers. The test that morning wasn't just successful, it was flawless. The B-24 climbed to altitude effortlessly, trailing faint streaks of rocket smoke behind it. Within weeks, other squadrons began requesting JATO kits for their own aircraft. From the Pacific to the Mediterranean, reports spread of bombers jumping off runways that once doomed them to crashes. The transformation was immediate. In North Africa, the U.S. Army Air Forces launched JATO-equipped C-47 transports, carrying supplies and wounded soldiers from makeshift desert strips. The takeoffs that once required a prayer now required a button. In the Pacific, PBY Catalinas, lumbering seaplanes used for rescue and patrol, began using JATO to lift from calm waters where they would otherwise wallow helplessly. The rockets fired, the hulls skimmed the waves, and the planes lifted free, carrying survivors back to safety. For the first time, the boundaries of geography and terrain no longer dictated where American air power could reach. Meanwhile, in Europe, the Luftwaffe struggled to keep its rocket-powered Me-163 Komets operational. The aircraft were technological marvels in theory, but nightmares in practice, unstable, explosive, and unforgiving. Takeoff accidents killed pilots before they ever faced the enemy. German engineers, desperate for progress, began to wonder whether they had been chasing the wrong dream all along. Word of the American rocket takeoff assist reached them through scattered intelligence reports and captured Allied documentation. At first, they dismissed it as crude improvisation, nothing compared to the Comet's full rocket propulsion. But as more evidence arrived, test photos, footage, technical notes, disbelief turned to alarm. How had the Americans achieved stability? They analyzed the data, balanced thrust, solid fuel composition, synchronized ignition. Each discovery chipped away at Germany's illusion of superiority. Their own fuel systems were volatile liquids, prone to chemical reaction and corrosion. The Americans had solved that by using solid composite propellants, stable, safe, and powerful. At Peenemünde, Werner von Braun's assistants privately admitted the JATO concept was mechanically perfect. It didn't attempt to defy physics. It cooperated with it, and while Germany's scientists were burning through scarce resources to launch missiles, America's engineers were using small, reusable rockets to make flight reliable. That was the real revolution. The success of JATO wasn't measured in explosions or speed records, but in the thousands of takeoffs that quietly succeeded, day after day, across the world's most difficult terrain. For American engineers, it was validation of a philosophy, the idea that progress came not from spectacle, but from solving real problems. And for the German observers studying grainy photos of smoke-trailing B-24s, it was humiliation. They had thought themselves the masters of rocket science. Now they realized the Americans had mastered its purpose. The shock in Germany grew as more reports reached Peenemünde and Berlin through intelligence intercepts and prisoner interrogations. American engineers, it turned out, were now mounting JATO units not only on bombers, but on fighters, transports, and even experimental gliders. A technology the Germans had thought primitive was becoming universal. By late 1944, the Luftwaffe's research division finally obtained a clear understanding of what they were witnessing. Standardized solid-fuel rockets, compact, reusable mounts, and electrically triggered firing systems that never misfired. They studied photographs of Navy PBY Catalinas lifting off from calm water, aircraft that should have needed heavy seas to gain lift, and saw blue flame bursting beneath their wings like controlled lightning. It was precision, not brute force. Within Peenemünde, younger engineers began to question the direction of their own program. The Me-163 Komet was fast, but suicidal. The V-2 missile was a scientific triumph, but a strategic failure, devouring fuel and lives for little gain. JATO, in contrast, was sustainable technology. It worked in the field, it saved crews, and it could be produced by the thousands. Senior officers refused to hear it. The Reich's rocket doctrine was already set in concrete. Rockets were weapons of terror, not tools of aviation. But a few quiet minds, mathematicians, aerodynamicists, and chemical engineers knew what the film from America really meant. The enemy had already discovered the bridge between flight and propulsion that Germany had overlooked. When American forces overran the European launch sites in early 1945, they found laboratories filled with incomplete dreams, burned-out engines, wrecked comets, and technicians still calculating impossible thrust equations. The war was collapsing faster than their equations could converge. Then came the day that sealed their astonishment. Captured Allied intelligence teams brought with them working examples of JATO units, steel cylinders barely a meter long, still smelling faintly of burned cordite. German scientists gathered around them as if inspecting relics from the future. One engineer turned the casing in his hands, weighing it, and muttered, "Das ist kein Spielzeug. Das ist Vernunft. This is not a toy. This is reason." They opened one carefully. Inside was no exotic alloy, no unstable fuel. It was clean, logical engineering. A solid-grain propellant molded for even burn. A single nozzle machined with mathematical precision. Everything about it was reproducible. It was industrialized science, the very thing Germany's fragmented system could never achieve under the pressure of ideology. Werner von Braun himself, when shown a JATO unit during later interrogation under Operation Paperclip, admitted that the Americans' practical mastery of combustion stability had surprised him more than any nuclear or radar discovery. He understood instantly what it implied. If the United States could make small rockets safe, reliable, and mass-produced, then larger rockets would follow naturally, not as weapons, but as engines of exploration. And that was precisely what would happen. In the spring of 1945, as Berlin burned and Peenemunde's runways filled with craters, The last surviving engineers realized they were staring at the path their nation had missed. Germany had poured its genius into destruction. America had poured its into propulsion. The same forces that lifted a B-24 from coral sand would soon lift mankind into the stratosphere. When Allied scientists debriefed captured German teams months later, they noted a curious reaction. There was envy, yes, but also respect. Many admitted that the JATO program had achieved in 2 years what the Reich's rocket division had failed to do in 10. Integrate scientific theory into usable engineering. It was, in their own words, a triumph of modesty. That humility was new to them. For a generation raised on the myth of technological supremacy, seeing a simple steel cylinder outthink their vast research empire was nothing short of a revelation. By the time the war ended, the shock had turned to quiet admiration. The Americans, through practicality rather than spectacle, had proven that the rocket's destiny was not to fall, but to lift. And though the guns would soon fall silent, the engineers on both sides understood one truth that would define the coming century. The age of flight was over. The age of propulsion had begun. When the war ended in 1945, the victors didn't just divide nations, they divided knowledge. The great spoils of World War II were not gold or land, but scientists. Under Operation Paperclip, hundreds of German engineers and physicists were quietly transported to the United States. Among them were veterans of Peenemünde, men who had built the V-2, the Me-163, and Germany's early rocket engines. They expected to find a nation still fumbling with primitive experiments. Instead, they walked into a laboratory culture that already had JATO, Aerojet, and the Jet Propulsion Laboratory, a system that had turned experimentation into industry. At Wright Field, and later at White Sands, these German experts examined American rocket-assisted aircraft. They found familiar principles: thrust, combustion, burn stabilization, but wrapped in a simplicity and reliability their own designs had never achieved. The JATO bottles could be mass-produced, stored safely for months, and fired with absolute precision. It shocked them. One Peenemünde engineer, now working with the U.S. Navy, reportedly said, "We had the mathematics, but they had the method." He wasn't wrong. The Americans had built not just rockets, but processes. The Caltech-Aerojet partnership had proven that science could move seamlessly from university to factory floor. Under Theodore von Kármán's direction, experiments that began in Pasadena classrooms became operational equipment within months. No totalitarian bureaucracy, no secrecy-driven fear, no political oversight, only engineering discipline and creative freedom. The Germans realized too late that this was America's real weapon. Organization. Where their research had been centralized and militarized, the American model was distributed and cooperative. Scientists worked with private industry, civilians partnered with the army, and innovation flowed both ways. It was democracy as a research method. In the post-war years, this structure evolved rapidly. The Jet Propulsion Laboratory, once a dusty wartime annex of Caltech, became the epicenter of American rocket science. The engineers who had perfected JATO now turned their attention to guided missiles, sounding rockets, and, eventually, space exploration. But for the German scientists now working under U.S. supervision, the emotional impact was personal. They had spent their careers designing machines of destruction, weapons meant to terrorize cities. Now they stood before American rockets designed to lift planes, launch research probes, and explore the upper atmosphere. One of them, after examining a JATO schematic, remarked quietly to his colleague, "We burned for death. They burned for flight." That single observation captured the moral divide that separated two visions of progress. In occupied Germany, Allied reports revealed how the Nazi rocket program had devoured resources and lives. Tens of thousands of forced laborers had died in underground factories at Mittelwerk to produce the V-2 missile. In contrast, Aerojet's California plant had been staffed by engineers and volunteers, men and women working under bright lights, paid for their skill, not enslaved for it. The difference was more than ethical. It was structural. Germany's science had been shaped by command, America's by curiosity, and as the post-war years unfolded, that difference became destiny. The United States didn't just inherit the German rocket legacy, it absorbed it, refined it, and expanded it. Von Braun would go on to design the Saturn V that sent men to the moon. But the foundation, the idea of rocket-assisted flight, of modular, practical propulsion, was already American. For the German scientists who once believed they stood at the pinnacle of technology, this realization was humbling. They hadn't been surpassed by magic. They had been surpassed by method. In the years that followed, the jet-assisted takeoff experiment evolved quietly into a cornerstone of modern aerospace. While the world celebrated the atomic bomb and the jet engine as symbols of victory, few realized that the humble JATO rocket had already opened a different frontier, the science of controlled propulsion. By 1947, American engineers had refined JATO units into compact bottle rockets, usable on nearly any aircraft. The Navy's P-2V Neptune patrol planes became the first to rely on them routinely for overloaded takeoffs. In one legendary test, a JATO-boosted Neptune took off from Hawaii and flew non-stop to Ohio, 4,600 miles, setting a record that stunned military observers worldwide. The flight's success was proof of concept. With rockets, airplanes were no longer bound by runway length or geography. At the same time, the knowledge gathered through JATO research flowed directly into America's next great leap, guided missile technology. The same engineers who had tested those steel cylinders in the California desert now applied the principles of combustion stability, thrust vectoring, and solid propellant chemistry to new projects at White Sands and JPL. Within 5 years, the United States had functioning surface-to-air and air-to-surface missiles, all descendants of that early wartime breakthrough. For the Germans working under Operation Paperclip, this was a haunting realization. They had once been the world's rocket pioneers, yet the Americans were now advancing faster, safer, and with far greater resources. Worse for their pride, the U.S. had accomplished it without relying on slave labor or secrecy. A 1946 report, written by a former Peenemünde chemist working at Wright Field, captured that sense of astonishment. They solved stability by patience, not by accident. They standardized what we theorized. It was an admission that the race for technological mastery had been lost long before the war ended. Meanwhile, in Japan and Europe, captured film reels of JATO tests circulated among post-war engineers. To nations struggling to rebuild their aviation industries, the images of aircraft leaping skyward under rocket thrust were mesmerizing. Not as weapons, but as symbols of possibility. In Japan, scientists at the University of Tokyo later cited American JATO research as their first real encounter with applied rocketry. Engineering designed for efficiency, not destruction. In the United States, JATO's legacy continued to spread. The Aerojet Corporation, born from the wartime Caltech project, expanded into missile production, research rockets, and eventually spacecraft propulsion. By the 1950s, its engineers were testing hybrid engines for supersonic aircraft and space boosters. Each success traced its lineage back to those first desert tests at Muroc, when fire and ingenuity had lifted a heavy bomber from the Earth. But perhaps the greatest transformation came not in machines, but in mindset. JATO had proven that rockets didn't have to be monstrous or mystical. They could be reliable, repeatable, and safe. That simple truth would become the philosophical seed for America's space age. For the German scientists watching this unfold, admiration replaced disbelief. They had seen what ideology could build and destroy. In America, they were now witnessing what freedom could create. When Wernher von Braun later stood at Cape Canaveral in the 1950s, watching the first Redstone rockets launch toward the heavens, he reportedly turned to a colleague and said, "We began with a weapon. They began with a helper." That single distinction captured everything. The Germans had used rockets to make war faster. The Americans had used them to make flight freer. By the time the jet-assisted takeoff project faded from military headlines, its legacy was everywhere, in jetliners, missiles, and spacecraft that all owed something to those steel cylinders of fire. And though the war had ended in ruins, one truth had survived the ashes. When the world learned to guide fire, it could choose to destroy or to ascend. When German scientists first watched the film of that B-24 rising into the desert sky, they didn't just witness a new machine, they witnessed a new philosophy of power. For centuries, flight had depended on the slow mastery of air and wing, of lift and drag. The rocket was something else entirely. Raw energy, unshaped and untamed. Germany had used that energy to strike cities. America had used it to help aircraft leave the ground. The difference was subtle in appearance, but profound in meaning. One sought domination, the other sought control. Jet-assisted takeoff was more than an engineering trick. It was the moment humankind learned that fire could be directed, rationed, and applied with purpose. It marked the first union of rocket thrust and aeronautical precision. A small step that quietly bridged the age of propeller and the coming age of space. In the chaos of war, it had seemed like a footnote. Yet every launch that followed, every missile, every spacecraft, every jet booster, carried the echo of those first JATO bottles burning across the California sky. When the dust settled, the Germans who once dreamed of conquest now stood shoulder to shoulder with the Americans who had mastered cooperation. Together they turned weapons into engines, and competition into collaboration. And in that strange peace born from destruction, the true lesson of JATO endured, that progress isn't measured by how high we climb, or how fast we burn, but by how wisely we learn to aim our power. Because in 1942, when 8 small rockets lifted a bomber out of the desert heat, the world caught its first glimpse of a new kind of flight. One not bound by runway, nation, or war, but by the endless idea that even fire, once feared as chaos, could be taught to lift.